right, so calculating the pH at equivalence of a titration. Obviously, if we weren't told it was at equivalence, we'd have to work out the number of moles of acid, the number of moles of base, see if they're equal or not. In this case, we've been told we're at equivalence. So what we're going to do is we're going to work out the number of moles, and we have a weak base, right? So the number of moles of weak base that we have, we've only been given the concentration of the weak acid, but we know the number of moles is going to be equal, so we're going to use that to work out the amount of volume of our strong acid that we've added. Why do we need this? Because what is happening in this case, our weak base is ammonia. So ammonia is going to get titrated by strong acid. So neutralization will occur. Okay. But because our base is weak, the product of that neutralization, the conjugate acid, is in and of itself a weak acid. So we're going to have to consider the hydrolysis of that ammonium, in this case with water. Um, so that's going to require an ice table. Okay. So this weak acid then is going to go on to react with water, and that will be a reversible reaction because it's weak. So something a little bit like this, right? Is going to reform the conjugate uh, base plus hydronium. So that is where our actual final pH is going to come from. So that's why it's at equivalence. Why at equivalence? Sorry. If we have a weak base being titrated by a strong acid, our pH at equivalence is going to be acidic. And on the flip side of that, if we have a weak acid being titrated by a strong base, our pH at equivalence is going to be basic because it's coming from the conjugate base of the weak acid. Okay, so let's go ahead and work out how many moles of what we have then. So first of all, let's take that concentration of ammonia. So 0.4386 molarity is moles of ammonia per liter. Take the volume that we actually have, which is 80 milliliters, and we're going to have to convert that into liters. So I'm going to run out of space here. 1 milliliter is 10 to the minus 3 liters. All right, so number of moles of ammonia we have is 0.035088. Okay. So if we have the same number of moles of, in this case, the nitric acid, and we know the concentration of the nitric acid, we can work out the volume of the nitric acid, 0.035088 moles of NO3. Again, use that concentration as a unit conversion factor, right? So we got 0.7280 molarity. So that means there's 0.7280 moles of nitric acid per 1 liter. So now I've calculated the volume in liters. I should have added an equivalence of my acid. I've just got to convert that to milliliters. So 1 milliliter is 10 to the minus 3 liters. I'm going to run out of space here. Don't need that. So that's going to tell me that I have added about 48 and change milliliters. Let's just go up. Okay, so why do I need this volume? Because I need to know my total volume for my new concentration, right? So my initial, if I could spell, initial concentration of my conjugate acid, my ammonium, which is what we're going to be looking at for this hydrolysis reaction, is going to be the number of moles of ammonium that we've been generated, which is the same as the number of moles of ammonia that had to be neutralized. Divided, and this is where sometimes mistakes are made, by the total volume, because we've added literally more solvent, right? So our total volume is going to be, what was it originally, 80 milliliters plus the added acid also is going to contribute to that total volume, and we're going to have to convert that into liters again because concentration is moles per liter. What does that give me? I don't know. Been a little bit slack with drawing my lines in here, for which I do apologize. I got excited. Um, So let's see, moles, milliliters, yada yada yada, milliliters, milliliters, moles per liter. We should end up with our initial concentration of ammonium as 0.2737 moles per liter. So now we're just doing an ice table for uh, the hydrolysis reaction of the ammonium cation, right? So I could even go ahead and write a Ka expression for that, right? Ka is the concentration of NH3 times the concentration of hydronium. That's what we're going to want to know. Whoops. Divided by the concentration of ammonium. It's going to equal Ka. We haven't been given Ka. Hang on. Ka. Well, I've got pKb, so pKb. And again, there's a many ways to do this, right? Because there's so many expressions that relate Ka and Kb, pKb, pKa, etc. I'm going to do this way. pKa plus pKb is pKw, which is 14. So pKa is going to be 14 minus whatever pKb was, which is 4.75. That gives me pKa is 9.25, but I don't want pKa, I'm just going to want Ka, but we know what P means. P means minus log, so Ka is going to be 10 to the power of minus pKa. 10 to the power of minus pKa, which we can totally do. So 10 to the power of minus 9.25 gives me Ka. 5.62 times 10 to the power of minus 10. This is all like last chapter stuff. So now I can do this, right? Just stick that on my K expression because I know I'm going to do an ice table and that's what I'm going to be looking at in a minute. Okay, so for my ice table then, I am looking at the reaction of the weak acid ammonium with water. The products of that is going to be ammonia and hydronium, and that is where my pH less than 7 is coming from in my equivalence point. So we know how to do this. We've done it before. So my initial concentration of ammonium, which is what I just worked out, was 0.2737 moles per liter. Initially, I shouldn't have any ammonia because it has been neutralized. And I'm going to assume zero hydronium, although of course there is going to be some small amount from the hydrolysis of water. So as my ammonium reacts with water, I'm going to lose X moles of ammonium and gain X moles of ammonia and X moles of hydronium. So my equilibrium values in terms of X, which is going to be the concentration of hydronium at equilibrium. So I'll be solving for that because that's what I want to know to find out my pH. Will be so I can substitute those into my Ka expression. So Ka is going to be X times X divided by 0.2737 minus X, and that is going to be equal to my Ka value, which is 5. I wonder if I've still got that on. Yes, it's still there. Ha! Oh, that's the small victory. So, of course, algebraically, we know by now we can simplify this. X times X is X squared. And we know we can make the X a small approximation because, honestly, that is going to be like times 10 to the minus blah blah blah. So 0.2737, if it's like 10 to the minus 4 or something for X, we'll know in a minute, that's going to be nothing in terms of the number of sig figs. So let's go ahead and do it. So what we're actually going to be solving is X squared over 0.2737 equals this. So then my X is just going to be the square root of this times, whoopsie, I can't count, 0.2737 square root of that. So if you prefer, take this times this and do it to the power of half. That's a useful trick when you're trying to type on a computer. So I get that X is equal to 1.24 times 10 to the power of minus 5. So again, I'm not going to do any further calculations for my x's small approximation, because I've got a lot of experience with this now. I'm just going to look at this number. It's to the magnitude of 10 to the minus 5. So if I look at my minus x there, to the number of sig figs I've got in the 0.2737, it makes not a whit of difference. So remember, that was my concentration of hydronium at equilibrium that I was solving for. So my pH is minus log of the concentration of hydronium. So minus log of, yep, this comes out to be a pH of 4.91. So acidic pH sounds good to me, sounds reasonable. And that's all there is to it. So the more we practice these, the easier it will get, I promise.